So we start with a new set of lectures by Cline. So Jim is a professor at McGill University in Montreal, and you have met him already these last few days, and he's going to tell us about composite dark matter, dark atoms, and so on.
Thank you. It's great to be back here. I was last year in 2006 giving lectures on baryogenesis and string cosmology. Some of you heard me say. Actually, somebody asked me, what's changed since then? And I guess thinking about it, the main thing is that it's much harder to hike now than it was then, for some reason. So I'm going to start today with dark atoms. And then next time we'll get into strongly confining theories for composite dark matter. So dark atoms are very simple. You just think about one at a time. But when you start thinking about collective effects, then it gets very complicated. Throughout these lectures, I'm going to focus on a few issues, mainly relic density, cosmological constraints. So these are issues that will be common to all the different kinds of composite dark matter, direct detection, and in some cases there's also indirect detection. I'll talk less about accelerator signals, but I will have a few interesting examples of accelerator signals. It's just something I've worked on less, so I'm going to focus on the cosmological aspects. So let's start out with the basic picture and establishing some terminology. So I'm just going to try to put primes on everything to distinguish it from a normal atom. And so we will imagine that our dark atom, which I'll call H prime for hydrogen prime, is just consisting of bound states of dark proton, dark electron with a dark photon. In the earliest days of this subject, going back to 1966, people thought about mirror sectors, where we had a full copy of the standard model, not just these particles, but everything. And so that was one of the earliest theories of dark matter. I'm going to focus on, and what people have tended to do in recent years is just simplified sectors, so that we can just think about a dark sector that only has those particles for the moment. And first, I'm going to assume that the dark photon is massless, but we'll come back to what are the effects of a massive dark photon in a little bit. And let's just recall what some of the important quantities are for characterizing a dark atom. Well, there's the Bohr radius. How big is the atom? So you'll remember from your quantum mechanics that it's 1 over, is there a factor of 2? No, it's just the fine structure constant and the reduced mass. What are those? So I'm going to use, instead of E prime, I already used E prime for the particle. So for the charge, I'm going to use G prime. Okay, so there's the fine structure constant in the dark sector, and the reduced mass, of course, of the system is just the reduced mass of the dark electron and dark proton. And oftentimes we're going to assume, like in the real world, that this might just be close to the dark particle, the dark electron mass, because without lots of generality, I can always assume that the dark proton is the heavier of the two particles. You know, that's just a definition of which one is positively and negatively charged. So one other quantity, why don't I write it up here to, since I have such limited real estate. Let's define the ratio of those two masses. So we can define that to be bigger than 1. Another important quantity is the binding energy. And so I will call that B sub H prime. And that's given by alpha prime squared over 2 times this reduced mass. Or if you want to express it in terms of these ratios, that turns out to be approximately the mass of the dark atom times alpha prime squared over 2. And then we have this ratio R over 1 plus R squared. Oops. Okay, so those are some of the quantities that we're going to be interested in. And typically, we will assume that the binding energy is much less than the mass of the hydrogen atom. That's just an assumption about weak coupling. So if you just work it out, well, what is the mass of the hydrogen atom? Of course, it's the sum of the mass of the constituents, but we have to subtract the binding energy. Okay, so we just want to say that this binding energy is making a small contribution. And if you work it out, that puts a constraint on the how strong the coupling can be. So alpha prime has to be less than square root of 2 times 1 plus R. And yeah, so in the extreme case where we have degenerate electron and proton, that would be square root of 8. And anyway, so you see it's a rather moderate requirement on, yes.
Thanks. Is there some physical reason that the mass of the proton should be heavier than the mass of, should be larger than the mass of the electron?
That's just an assumption because I can, whichever one of these is the heavier particle, I'll call it the proton. And then I don't care whether it's charge plus or charge minus. I can, you know, that's a choice of the sign convention of G prime.
Got it. And then are we assuming that the dark protons are composite particles themselves?
No, not at this point. So good question. In the simplified models, we can just assume that they're elementary particles.
Okay.
But of course, in a full mirror sector, then they would be composites, just like the standard model. Yes, thank you for the question. I might not notice, so if you have questions, please interrupt me. I'm not paying attention. Yeah, so you see, this is a very mild assumption on the that the coupling shouldn't become too strong. Well, the reason I mention it though is that in the literature, you often see people, instead of plotting things with respect to alpha prime, they plot them with respect to the binding energy, and then they have to put you know, shaded out regions where it wouldn't make any sense because they're violating this kind of constraint, and then approximations would just be breaking down. Okay, so I'm going to erase this. And well, so that's the simple part because you know all that from quantum mechanics. So we're just not used to thinking of all of these quantities as being variables. We can adjust their values in this dark sector. Well, let's talk about cosmology. And there's going to be an important parameter that enters a lot of the analyses, which is the dark sector temperature. which need not, of course, be the same as the visible sector temperature, because if these two sectors are really secluded from each other, then even if they start out being the same temperature, they will quickly, T prime will drop compared to standard model temperature because of all the entropy dumping that will increase the standard model temperature relative to the dark sector. So we're going to define this ratio, which in general, it changes with time. So if you're being careful, you should say at what cosmological epoch do you mean when you give a value of C. So let's put a little timeline for how things might be happening, where suppose we start off with inflation, and then T prime will have some initial ratio. So depending on maybe the inflaton couples more weakly or even more strongly to the hidden sector. So I could start out being bigger than 1. Then the next important event would be the freeze out of the annihilations of the constituent particles. So these will annihilate to dark photons. And that will happen at a temperature which, you know, when you solve the Boltzmann equation, you typically get a freeze out around temperature of the mass of the particle divided by 20 or 25. And so the dark proton is going to freeze out earlier than the dark electron, unless they're degenerate. And then the next important thing, of course, would be recombination in the dark sector. So we have then the constituents recombining into atoms. And that we expect to happen when the dark sector temperature is of order I should put squigglies for these temperatures, order the binding energy. And then one more important event, of course, well, this I mentioned because, well, this is one of the things that gives us a constraint. I could have mentioned nucleosynthesis somewhere on here as well, but I'll just mention CMB for now because we'll quote a constraint on this ratio. Okay, so by the time we reach the CMB temperature, which is around an electron volt or so in the visible sector, then we're going to have some ratio depending on what we started with, and it turns out even if you started with equal numbers, there's enough entropy dumping into the standard model, assuming this was, say, greater than the QCD phase transition, that you will dilute this ratio down to an acceptable value. What is the constraint on it? I think you know, you've heard about NF, the effective number of light neutrinos being constrained by CMB and VVN. And so that constrains the value of the ratio to be less than 0.57. And so typically when people build models and they want to have a significant dark photon population, they'll assume that this is of order 0.5. Yes.
Thanks. I don't understand why, if we're not saying anything yet about the relationship between the dark sector and the standard model, how an effective, delta N effective is going to put a constraint on the dark sector.
Well, it's just, I mean, we know we can't have more dark photons increasing the Hubble rate than a certain amount, right? So, I mean, that's a constraint, no matter what the interactions were between the two sectors.
Okay, so the constraint is coming from the rate of expansion.
Exactly.
Okay, thank you.
Yeah. All of these delta NF constraints are just from the fact that the Hubble rate would, so it goes like square root of the radiation density. So if you add extra contributions to the radiation density, then you're going to increase the Hubble rate. That will screw up Big Bang nucleosynthesis. It will screw up the acoustic peaks, CMB. Okay, but I'll just emphasize that even if psi I was equal to 1 at inflation, this would be satisfied automatically. By evolution of the dark photons, say during CD phase transition. Because then you get a huge increase in the entropy in the standard model as all these quark and gluon degrees of freedom collapse down to just a much smaller number of degrees of freedom, transfer their entropy into the standard model. And so that that lowers this temperature ratio. Okay. So another very important quantity for characterizing the cosmology is the ionization fraction, because at this event of recombination, it's not 100% efficient in general. It depends on the parameters of the model. So we'll define an ionization fraction, which is the number of dark electrons over dark atoms that form. And I'm going to assume for now, let's assume that there's no asymmetry, even though, yeah, let's assume that there's no asymmetry in the number of electrons and protons left over, which is, well, you could just think there's a charge neutrality of the universe in the dark sector. And so this ionization fraction plays an important role for some of the constraints that we'll talk about from cosmology. And to compute that, you need to solve Boltzmann equations. Because there are a lot, so this process, I mean, this is a highly oversimplified picture of how recombination takes place. In the real world, there's a whole series of reactions which contribute to recombination involving the dark photon, and it's complicated, I'm not writing them all down. Instead, I'm going to refer to papers that did this and show you the results. Yes.
So I understand that right now we're just saying that we have these equal numbers of dark electrons and protons. But with this mass splitting, where we have this freeze out with these different temperatures for each species, I mean, if I have highly non-degenerate masses, I could run out of dark electrons or something like this, right?
That's right. So in that case, yes, in that case, what we're really thinking about is asymmetric dark matter. And I'm going to show you in a bit that, so just like in the real world, we know that the baryons that we're comprised of are not the baryons left over from just annihilation. So there's not equal numbers of baryons and antibaryons in the universe. There's an asymmetry. That's most likely going to have to be the case for the dark atoms. And I will motivate that statement in a little bit. So actually, these are the ones that are, these are the net numbers. And I'm assuming that the symmetric components got annihilated away to a very high degree from these processes. And the only thing that's left over is the asymmetry between particles and antiparticles.
Excellent, thank you.
Now, thanks for that question. I knew I was kind of floundering when I was trying to explain what I meant here. So I think that clarifies it. So let me just, oh, and incidentally, I'm saving time here. You notice I'm not writing any references here. You have all the references in my notes. So just because it would take a lot of time to write them here, I'm going to omit references, and you can look them up if you want to. But so there was an original paper on this subject by David Kaplan et al. I'll mention some references. And then another one by Chris Sigurdsson and Francis Jens here, Racine, where they did this job of solving the Boltzmann equations. And then in one of my papers, we did an analytic fit to the results. Actually, we did an analytic fit to the results of the first paper. I'm just trying to make fits to their numerical results. And so we got an expression like this for the ionization fraction. Okay, so of course it can't be bigger than 1. And if it's smaller than 1, then it's roughly given by this quantity. I think we're assuming that R is much greater than 1. And then that was followed by the calculations of Sigurdsson et al. And they gave an expression for this, actually. And it pretty much agrees with what we deduced numerical from fitting the numerics. They wrote it differently, but parametrically, it's the same. So if you just plug in the formula for the binding energy, you see that these match in the large R limit. Okay, so there's one peculiar thing here. So you might think that if you increase the binding energy, that's going to increase the efficiency of recombination. But actually, it's making a bigger ionization fraction. So that's kind of counterintuitive. I'm not sure why that is. I think it's a kinematic thing, because if you look at this version of the formula, large binding energy actually, large binding energy, let's go to the opposite, corresponds to small r. Actually, okay, so anyway, I don't have an intuitive explanation for that. I have to think about it harder.
And for a larger binding energy, I'm thinking over here. If for a larger binding energy, I'm thinking I have a deeper potential well for my electron to fall into, so it's easier to create these dark atoms. Is that the intuition, or? Well,
that's the paradox, right? Because this is saying that larger binding energy is leading to a larger ionization fraction.
Right, so more efficient creation of dark atoms, no?
No, the ionization fraction is the number of, it's the fraction that are not in atoms.
Right.
Yeah. So that's counterintuitive, although, I mean, if you just look at the dependence on coupling constant, then that makes sense. The bigger the coupling constant, then the fewer ionized particles. Then another one that's counterintuitive is why does it care so much about the dark photon temperature? If you take away all the dark photons, then ionization, the ionization fraction goes to 0. Oh, so that makes sense, right? Because you would think that dark photons would, like dark photons interacting with these particles might. Okay, I guess that makes sense. Anyway, you can see this is not an aspect of the problem that I actually worked on. I'm reporting results from these other papers. So I think I'm not going to say any more about ionization fraction. So now let's talk about some constraints where that becomes relevant. And so one that you've heard about is the bullet cluster bound. And so that's bound on the self-interaction cross-section of dark matter, that is dark matter with itself. So self-interaction. It has a cross-section divided by the mass of the dark matter. Has to be less than something. I forget what the number is, but it's something on the order of few barns per GeV. And now you can see that if you had too large an ionization fraction, this is going to be violated, because if we have just scattering of dark protons with themselves or dark electrons with themselves, of course, this leads to an infinite cross section, assuming it's a massless dark photon, because this is Coulomb divergence in the Coulomb cross section from very long distance scattering. Of course, those very very long distance scattering are also very small angles, so they probably don't count too much, but nevertheless, this leads to a very large cross section. Yes.
If you have a rich dark sector with lots of types of dark sector particles, doesn't the bullet cluster bound get loosened a whole lot?
Yeah, so if I have, that's kind of the point I'm coming to, is that if I had a subdominant component of this dark atoms as being dark matter, then I can, so it's like around maybe 30%. If it's less than 30%, then you can be okay with the bullet cluster bound.
Okay, got it. Thanks.
Yeah, and so that's basically what we want to say here, is that we want the ionization, because any ionized particles, if they were all in the dark matter, they would violate the bullet cluster bound. So that puts a constraint on the ionized fraction. Yeah, so supposing the ionization fraction was equal to 1, so all the particles are still ionized, then you find a constraint on the coupling, which is 10 to the minus 3, depending on the mass of the dark atom. It goes like the 3/2 power of the dark atom. I'm going to show that first figure. Yes, thanks. So that was worked out. This bound that I'm talking about here was worked out in this reference as the red line. But what this reference didn't do is, so they made the assumption that you have a fully ionized dark sector. But you want to know, well, is it really fully ionized? Because we have this formula for the ionization fraction. And so what I've done is I've added to their constraint these two lines, which show you where you would need to be for a fully ionized dark sector, or one which is only ionized at the 10% level. And if it's only ionized at the 10% level, then you know you have a small enough number that you will at least probably evade the bullet cluster dump. Maybe you need to be a little bit higher, but roughly you're safe in this region. And so the real excluded region, by the way, this is the coupling versus the mass. The real excluded region is just this triangle instead of everything above the diagonal line. Okay, thanks. So another cosmological constraint, and this was worked out by C. Racine and other collaborators, is called dark acoustic oscillations. And this is the analog of baryon acoustic oscillations. I suppose people didn't talk about BAO in these lectures because they were talking about dark matter, but probably you're familiar with it. This is just the fact that at the time of the formation of the CMB, the baryons and the photons were a tightly coupled fluid, and so you get sound waves in the baryon photon fluid. And so these show up as kind of an analog to the Doppler peaks of the photons. They show up as these kind of mini Doppler peaks in the matter power spectrum. And so these have an effect on not only the matter power spectrum, but also on the CMB itself. So now we have, if we have also in the dark sector, the dark baryons, and it requires the dark photon plasma in order to provide the pressure, then those dark acoustic oscillations are going to add to the conventional ones, and they're going to increase the effect beyond what's allowed. And so when people did this analysis, they assumed that you were nearly saturating the bound on the ratio of the temperatures. Sorry, that's 0.5, so that they could get the maximal possible effect. And they also assume that instead of dark matter being, dark atoms being all the dark matter, the dark atoms were a fraction. I'll call it F int to distinguish it from the ionization fraction of the total dark matter. And so under those assumptions, then they could get constraint on the interacting part. And they found that it has to be less than about 0.05. Whereas these constraints rapidly go away if If the temperature ratio is much less than that, then of course you remove this effect. Marco, can I show the next? Sure.
I'm not sure what you mean when you say the dark atom fraction of total dark matter. Like, I'm talking about dark atoms versus these dark protons and electrons.
No. So I'm assuming that most of this, say we have 95, or yeah, for instance, we have 95% standard cold dark matter, it's just some WIMP. And say 5% dark atoms. Because the standard CDM wouldn't have this effect at all. It doesn't have any pressure. So it's just the fact that the dark atoms can have pressure with the. Let's see, how do I advance this now?
Click on PDF and yes. And then scroll.
Okay, thank you. So here's some examples of constraints from that original paper on the alpha and the dark sector. And they plot it as a function of the dark electron mass, assuming a dark atom mass of GeV. So they're also in the limit, you see, where the dark electron is much lighter than the dark photon. And here I'm showing you these gray regions are the ones that they are constraining by this effect, depending on whether. So here's a case. Yeah, so here's a case where psi is saturating their bounds, but they're only they only have 2% of the dark atoms as the total dark matter. So they get these regions which are ruled out by dark acoustic oscillations, and some region that's still allowed here. If I showed you their other plot where they had allowed for 5% here, then it wipes out the whole region. Here you see that this ruled out region moves downward and it opens up this part of the parameter space if I lower the dark temperature by a factor of 3/5. Oh, here's another thing I don't understand. Why is there this window here between two ruled out regions? I asked Francis Young, but I haven't heard back from him. So this is more of the complications of doing these kinds of analyses. Oh, yes.
What would the presence of dark acoustic oscillations be able to tell us about the formation of large scale structure, if anything?
I think it's just that they can't have an influence on it because we already have constraints on size of these oscillations, so they cannot have a significant influence on it, I think.
So do the dark acoustic oscillations just linearly add with the baryon acoustic oscillations?
I believe so.
Okay, got it. Thanks.
I guess for putting this constraint on the fraction of dark matter that can be in the form of dark atoms, one needs to assume a fiducial value for the strength of the quantum interaction between the dark electrons and the dark photons. No? This is assuming some fixed value for the cross section. Or
Well, the cross section is determined by the coupling strength and the masses. So
yeah, but what you wrote on the blackboard is instead a limit on the fraction of dark matter in the form of dark atoms.
yes,
So for I guess this is assuming some fixed value for the strength of the interaction.
no, but
Some fixed value of
anywhere on this
quantum.
plot, the strength of the interaction is determined by these parameters that are given,
Okay.
because it's just a function of the coupling and the masses. So anywhere on this plot, you know what all the masses and the coupling, so you know what the interaction strengths are.
Okay. So okay.
Okay, thank you.
You want to pass the mic to?
So this remaining 95% or so of dark matter, we're saying does not interact with itself at all. Is that?
Well, the standard assumption for cold dark matter is that it has negligible self-interactions and that it doesn't have any radiation bath that it's interacting with.
Okay.
Okay. Yeah, so now actually I will come to self-interactions. And did anybody talk about the small scale structure problems of standard CDM and how self-interactions can help you, dark matter self-interactions can help you with that? We talked about that, I'm curious.
And we
Oh, thanks. Great. So I don't probably need to remind you of the motivation for these self-interactions. But I'll just, let me write this again. So if you have dark matter self-interactions, which are, it always is expressed as cross-section over mass because smaller mass dark matter is more abundant and therefore its rate of self-interactions will be bigger. So sigma over m is the figure of merit. And if you have something of this order, and you probably remember, people like to use either centimeters squared per gram or barns per GeV, I guess, depending on whether they're particle physicists or astrophysicists. The actual ratio, I believe, is 1.7, but it's approximately a factor of 2 difference. Okay, so this is still below the bullet cluster bound, but it's close to saturating it. And this is the target for having significant self-interactions for solving the small scale structure. Small scale structure problems of standard non-interacting cold dark matter. And from a particle physics perspective, that's a huge cross-section. That's sort of similar to strongly interacting like protons. Oh, and let's see. And did she also talk about the fact that preferably many people think that a velocity-dependent cross-section is better? So let me mention that. So, you know, one of these problems is the core problem. The fact that standard CDM simulations predict very cuspy dark matter profiles, whereas so dark matter density is a function of radius. Observations suggest chord ones. And one of the observations is that dwarf galaxies and Milky Way-like galaxies have more strongly chord profiles than larger systems, which means clusters of galaxies. So when we write this kind of relationship, some people think that, well, this number would be good for the smaller systems, but we would prefer a smaller number for the larger systems. And this suggests velocity dependent cross section. Such that because in clusters of galaxies, the dark matter is also moving faster. So we have a higher dark matter velocity dispersion. Whereas dwarfs and Milky Way, in these systems, you have velocity dispersions on the order of 10 to 100 kilometers per second. Whereas in clusters of galaxies, we have more on the order of 1,000 kilometers per second. So I will show my next slide, which is one that I actually didn't put in your lecture notes. Maybe I will add it, but there was a nice review article by Sean Toole and Haibo Yu about this whole subject. And so I'm showing you one of their figures where they plot cross-section versus the velocity of the dark matter. And here they're indicating the ranges that I just wrote down on the blackboard. They're also showing theoretical predictions for various models and various approximations. So this is kind of the typical velocity dependence that you might like to have to best fit these systems. And so what I want to show you what dark atoms predict, because dark atoms, since they're big fat fuzzy objects, they naturally do tend to have a big cross section. It's a cross section of order the Bohr radius, and remember the Bohr radius is going like 1 over the coupling. So you can get very large cross sections from dark atoms. Actually, let me go to, I'm sorry, Marco.
Yeah, I just adjusted. I'll share the thing from your head.
I forgot I was going to move on to the next one. Here is what here's what atom scattering looks like in the real world. So this is cross-section in units of the Bohr radius squared as a function of energy in terms of, well, this is the natural unit of energy for, this is basically twice the binding energy. It's called the Rydberg in atomic physics. And so you see that you do get a rather complicated dependence on energy, which, well, at extremely low energies, it's smaller, but you see at large energies, it is dropping off the way that one might want it to. What are all these different curves? Let's see. Okay, yeah, these blue and yellow ones, these are what you converge to when you add enough partial waves. So I'm going to describe this calculation. We're doing scattering of atoms and partial wave expansion. And you see what happens if I only add a few partial waves. I don't predict it very well. If I add up to 40 partial waves, then I get something that converges. And the thing it's converging to is actually also in good agreement with what's measured. Yes.
Just to kind of make sure I understand the big picture here. So we want more chord profiles in smaller systems, and smaller systems have lower velocity dispersion. And so we want a velocity dependent cross section because the lower that cross section is going to go up with lower velocities, and we want higher cross sections for more chord profiles. Is that how all these pieces fit together?
Yeah, I'll just skip to this one. This behavior, and I'll explain what these have to do with each other in a minute. But so this basic behavior where the cross section is going down with energy or velocity, that is what you would like in order, because then this means that the effective dark matter stealth interactions is becoming smaller, and so it's going to leave a more cuspy profile in the big system with fast dark matter.
Okay, so higher velocity leads to more cuspy profiles.
Yeah, basically it
Okay.
leads to the dark matter doing less.
Okay, which is what we want in bigger systems.
Yes,
Got it. Thank you.
thank you. So maybe we can just leave this for now, or is it too dark? If I mean, you could probably just leave it. I just want to say a little bit about how those calculations are done, because that's something I know about. And it's also, it was it's kind of fun and interesting thing, because it's just quantum mechanics. So let me just mention, in units of this Bohr radius squared, what you saw is that the cross-section range between, say, 30 and 300 in the visible sector in our real world. And so we can expect that in a general dark sector, dark atom sector, you might see something similar to that. And of course, we have this interesting energy dependence. So I'll just say again, for this problem, it's natural to use atomic units where the Bohr radius is the unit of distance. And this thing that I call E naught, it's just alpha prime squared mu H prime, which is twice the binding energy. And that's a unit that atomic physicists call the Rydberg. And in order to compute these cross sections, you have to solve the Schrodinger equation. And so it's convenient to rescale all the variables, energy and distance, to atomic units. And then the Schrodinger equation can just be written in this form, it turns out. So there's some scattering potential that depends on whether the atoms are in the spin singlet or spin triplet state. So you know what that refers to is it's the electrons. So we have two atoms, and their electrons could either be aligned, so that would be the spin triplet state, or they could be anti-aligned, the spin singlet state. The proton spins don't matter because the proton magnetic moment is suppressed by its big mass. I'm assuming for these calculations that we're in the standard model-like limit where the proton is much heavier. So anyway, it turns out that the interaction potential between two atoms, okay, so we have two atoms separated by a distance r, so they have some interaction potential, and it turns out it depends on whether they're in the spin or singlet or triplet channel. And this is something that's very complicated to compute. You need to use like Hartree-Fock to many body kind of techniques, but it's something that's been done by atomic physicists. So they've computed from first principles what these potentials should be, and then they've tested them against the actual data and validated them. So we think we know what these are, and the funny thing is, or the cute thing is that these potentials are independent of, once you express them in terms of atomic units, they're independent of all parameters in the limit that we're assuming here, where the dark proton is much heavier. These potentials don't depend on anything. So we can just take them and use them for our generalized dark sector. And then all the interesting dependence on parameters is in this simple function, which turns out to be r plus 2 plus 1 over r minus. So it's basically coming from something involving the reduced mass of the 2 hydrogen atom system. And this binding energy effect is coming in here. But in our case, it's also going to be independent of that because we're assuming weak coupling. So basically, you can compute any of these scattering processes, and they're going to be independent of the coupling except through the dependence on these units. So that's a trivial scaling dependence. And all the interesting dependence is just coming from this one coefficient. Yes.
I'm confused about the point that the potential doesn't depend on parameters. Could you say a little bit more about that, please?
Yeah, so when you do things in atomic units, and you compute these potential, you discover that they only depend on the kinematics, the ratio of the differences between. It's a non-trivial argument, so I would have to review what we wrote in our paper about it, but it's true that in the Born approximation, that these become independent of everything. I guess it's a little bit, I don't remember the details, but I'll try to remember and get back to you.
Thanks. It is the basic idea that when we have much heavier protons than electrons, we can treat these things like billiard balls.
Well, I think there's more to
Not
it
quite.
than that.
Okay, thank you.
Yeah. So, and so, this is just the usual trick that you can do in 3 dimensions. You solve for the wave function times r, and you get this simplified version of the gradient kinetic energy operator that makes it look like a 1-dimensional problem. Anyway, so you have to solve this for all these partial waves, and you have to do it separately for the spin singlet and the spin triplet channels. And then you have to add those contributions together, and you get these cross sections. And you just compute them to enough partial waves where you see that things are converging. So one thing I wanted to mention, though, is the difference between those 2 cross sections. Could you show that diagram again?
Zoom records only the screen. That's why.
Yeah. Okay.
Don't worry.
So I had 2 different kinds of cross sections here. This is the usual cross section. This is called the momentum transfer cross or transport cross section. So we could just call this the elastic cross section. This is the transport cross section, and you see that, and these are the results that you get when you do the calculation I mentioned for different values of this ratio. And you see qualitatively there's a similar behavior. But we smooth out a lot of these features, which are coming due, these features are coming about due to resonances in the various partial waves. So it's all due to the details of those potentials. Yes?
So what are the general differences between doing this calculation for a dark hydrogen with respect to the need for a standard hydrogen? Is it just this dark fine structure constant, or are there more subtle differences?
What I'm saying is that everything is just depends on these parameters, and in fact, the only non-trivial dependence is through changing the value of R, and all the other dependence we can get through just simple rescaling of the dimensional quantities.
Okay, so the new physics introduced by the dark sector is this function.
Exactly.
Essentially. Okay.
It's all that. Everything else is just pure standard atomic
Okay.
physics.
Mhm. Thank you.
So what is this transfer cross section? I guess you'll have to go back to the board now. It's just something that weights the differential cross section by the momentum transfer. If I just wrote this, that would be the ordinary cross section, no prime. But what we want to do is to weight it by something that penalizes the cases where we have almost perfect forward scattering. So if you have perfect forward scattering where the scattering angle is 0, then we don't really care about those for the purpose of erasing a dark matter cusp, because that really does nothing. And so a better measure of what's the real effective cross section is when you weight it by this factor that penalizes the uninteresting contributions. And usually people would write 1 minus cosine theta for that. But when you have identical particle scattering, then if you have exactly 180-degree scattering, in quantum mechanics, that's indistinguishable from forward scattering. And so by writing cosine squared theta here, then you also do the right thing for identical particles. Okay, so, and this is the quantity that also has smoother behavior as a function of energy. And so after we wrote our paper on this, there was one by Body et al., which took the analysis further, and they included the effect of hyperfine transitions. So we did pure elastic scattering. But another important kind of scattering is when you make a transition between spin triplet and spin singlet. So that's the hyperfine transition. That's something with that's a small energy. So you could say it's almost elastic. It's just got this small energy that's suppressed by 4 powers of the coupling. And anyway, when they took this into account, and can I have the screen again? And they did the fits. We found good fits to dwarfs versus clusters for a particular value of this hyperfine energy. By the way, you can just think of this as a different way of parameterizing the dependence on parameters, because this hyperfine energies, you can think of this as being another way of depending on the parameters for large R's. Anyway, what they did was they looked for fits to systems of different sizes. So this is in the plane of the coupling and the dark matter, the dark atom mass. And they find in order to fit data of the, so orange is clusters, green is dwarfs. You would get good fits to clusters versus dwarfs in different regions of parameter space if you had too small a hyperfine splitting, but for around 10 to the minus 4 of the atomic units, hyperfine splitting, then you see these nice regions of overlap over a range of parameter space. So here's an example of where you can use the velocity dependence of the cross section to get a good fit to different systems. Yes.
So if I'm not mistaken, it seems like all of this is requiring a Coulomb-like, at least potential, if not exactly a Coulomb potential.
Well, actually, this potential that I erased between atoms is not Coulomb-like because we have neutral particles. So it's something more, I should have brought a picture of that too. It's something more complicated. Well, it's something that has, I don't know, it's something for the spin singlet. I think there's a bound state. It's for the spin triplet. There's not a bound state. So it looks something like this. And yeah, there is some kind of Coulomb barrier at very short distances, but you know, these are complicated things that the atomic physicists had to calculate.
So I guess my question still holds, which is that we're assuming our dark sector atoms behave in the same way as our standard model atoms do in terms of the shapes of these potentials.
Well, it's not an assumption. This is, I was trying to say that this is totally theoretically sound concept.
Okay, so this is fully generic for any kind of dark sector that forms composite particles?
Well, I'm assuming that it's a U1
Okay,
here.
So it has to be a U1.
Yeah,
Okay,
right.
got it. Thank you.
Okay, well, I spent too much time on that. Let me say a few words about relic density. I said before that probably one would like to get asymmetric dark matter. Let me say a little more about that. And it's a natural thing to do because dark, in our model, dark proton number and electron number are conserved. These are just Dirac fermions. So it's natural to imagine there's an asymmetry. And one way you could do it is similar to, in fact, simultaneously to leptogenesis. You know, in leptogenesis, you have some heavy neutrino decaying out of equilibrium into Higgs and a light neutrino. Well, we could couple the same heavy neutrino, since it has no quantum numbers, to some, say, Higgs in the dark sector. Okay, so we have to do a bit more model building. We could have some of these decays also happening into the dark sector. And then you just have to adjust the the ratio of these Yukawa couplings. Let me say there's same Yukawa coupling. Then you see that the eta of the asymmetry in the dark matter compared to the ordinary baryon asymmetry is just going to be some function, say, of these Yukawa couplings. And so you can easily engineer the right asymmetry in dark matter through that simple picture.
Is that number conservation exact symmetry?
Yes, I didn't put anything into the model that would violate that.
Okay, so I guess it would become non-exact if your protons were composite particles and your quarks had non-degenerate masses or something like that.
Actually, I'm sorry, I was just thinking, right at this step, I've violated it. But I guess, so that there's some combined, now I have to assign a charge. It's probably, two different particles. I have to assign charges to those particles to conserve it. You were suggesting.
I was suggesting maybe the dark protons are composite particles and your quarks have non-degenerate masses, which would make that a non-exact symmetry, I think.
No, but even in the standard model, protons are composite particles, but they're still conserved. So the conservation of those particles then would come from the conservation of the constituents.
Isn't baryon number conservation an approximate symmetry?
Oh yeah, in the standard model because of this Valoron business, but
Right.
we could have a simpler hidden sector that doesn't have that complication if we wanted to.
Thanks.
Oh yeah, so I wanted to show you the next slide just to say why it's hard to do things without having an asymmetry. So what some authors did was to, okay, so I mean, if we didn't have an asymmetry, then we would just have the freeze out, the usual freeze out from the annihilations of the dark protons and the dark electrons. And so what these authors did was, this was Randall et al. Make dark matter charged again, I think was their paper. They just computed where would you need to be in terms of coupling and dark constituent mass in order to have the right relic density. Okay, so you would need to be there. But what I did was to superimpose on that plot contours of constant ionization fraction. And so you see, if you're along this, anywhere along this line, that's a model where the dark matter is still completely ionized. So if you get your relic density that way, you don't get dark atoms, you just get dark ions. So that's why you really want to have some asymmetry. Okay, so now let's talk about making the model more interesting, because so far we don't have any way to directly observe this dark matter. And actually, before I talk about that, let's suppose we have a dark photon mass. How do you get a dark photon mass? Of course, you know there's two ways. We could have a Higgs mechanism in the dark sector, or we could have this peculiar way of doing it called the Stuckelberg mechanism, where that's basically just writing down by hand a dark photon mass and then dressing it up as though it's still gauge invariant. And so you add this Stuckelberg field, which transforms under a gauge transformation Suppose that the gauge transformation in the hidden sector is in terms of some function phi prime. Well, then if I let the Stuckelberg field also transform linearly under that field, then of course those cancel each other. So that's a way of making a bare mass term for the photon gauge invariant. And so these are two possibilities for giving dark photon a mass. So the interesting question is, how big can the dark photon mass be and still have atoms? And well, if you want to answer that question, you have to solve the Schrodinger equation. So we would write down this Schrodinger equation. Instead of having a Coulomb potential, though, we would write a Yukawa potential. And here I'm doing that trick again where I write down the equation for r times the wave function to make it look like a one-dimensional problem. So in general, one would need to solve the Schrodinger equation and find out how big can m gamma prime be and still have, sorry, I guess I meant not to write 0 here, but energy at the bound state. So how big can m gamma prime be and still have a bound state, which would be e less than 0? Well, I just want to show you a cute way of very quickly. So one way you could do that, if you didn't want to solve it numerically, is you could do a variational calculation. Just make a variational ansatz. So psi e to the minus r over some number. And you could do the variational problem to make an estimate. So I did that, but then I realized there's an even simpler way. Use perturbation theory. And if we express for very small dark photon mass, we can express this as 1 minus m gamma prime r plus stuff. And when you do that, and then we have alpha prime over r in front, interesting thing happens. The r's cancel here, so the perturbation in the potential is just a constant. So we're doing perturbation theory where the perturbation is just a constant. And so then you know what the shift of the energy is. It's just the expectation value of the shift in the potential, and it's exactly equal to that constant. And so that very simple estimate would tell you that, okay, so then the change in the binding energy would just be minus that. Because the binding energy is just minus the energy. And so by demanding that the total binding energy remains positive, you would find that m gamma prime has to be less than alpha prime over 2 times the reduced mass of the electron and the proton. And well, if you try to saturate that limit, our perturbation expansion breaks down. So that's not quite right. If you solve the problem numerically, you find that the real limit is that m gamma prime has to be less than 1.2. But you see, it's it's the right parametric dependence. So you get the right order of magnitude estimate from that simple calculation. Yes.
When you use the Schugelberg mechanism, that's not something I've seen before. Is that something that we're applying only to the photon field? And it kind of leaves everything else the same, or what's happening there with our interactions?
Yeah, nothing's happening with interactions. It's just, as you say, showing up in the photon field. So, the gauge invariance, the gauge transformations on the electron and the proton, they're exactly the same. It's just that you've added a new field that is also shifting under the gauge transformation. It's kind of a cheat, but it's formally a correct way to maintain gauge invariance for U1 theory.
Okay, and could both fields, the original and the one that you're adding, could both of those have a mass term?
Well, the thing is, it's kind of like the Higgs mechanism where they're not, this theta field is not a dynamical field. It doesn't have an extra kinetic term. So it's really just the moral equivalent of the thing that gets eaten to give a mass to a photon in the Higgs mechanism. Another way to think about Stickelberg is if you go to the if you take the Higgs mechanism and go to the limit of infinitely heavy Higgs, so you decouple the Higgs, then you're only left with the Goldstone boson that gets eaten. So that's basically what you're doing with Stickelberg. It's you're writing down that Goldstone boson field and it's just getting eaten to give mass to the photon.
Okay, that helps. Thank you.
Well, let me just, in the last 5 minutes, so let me just mention the way of making these dark atoms visible to the rest of the world, the real world. And that is through kinetic mixing of the dark photon. This is something you probably talked about in previous lectures. Am I correct? So maybe I don't need to, I won't say anything. Oh, did they talk about Stickelberg mixing? Because no, okay. So that is an interesting variation. So in Stickelberg mixing, we have, in addition to the usual kinetic mixing term, we also assume that the Stickelberg field transforms not only under the dark gauge transformations, but also under the standard model gauge transformations with some parameter lambda. So here, I mean that the standard model gauge boson transforms with the gauge field, the gauge function phi. The dark photon transforms with phi prime. And so if you simply assume that the Stickelberg field transforms under both things, then you get something called Stickelberg mixing, where the change to the Lagrangian when you go to the diagonalized mass basis of the gauge bosons is, so you get a coupling of the standard model photon to the dark U1 current. I put a prime on it. That depends on the dark coupling and the Stickelberg parameter. But you also get the opposite thing, where the dark photon couples to the standard model current. And its coupling strength is the electric charge and some linear combination of these two small, presumably small parameters. So that's an interesting variation. And then now we can have direct detection of dark atoms through say exchange of the photon. So here we have exchange of the photon. It couples to the dark current with this small lambda coupling. But the charges of the electron and the proton are opposite to each other. Okay, so here's the visible proton. Here's the dark atom. We're going to get canceling contributions from the two constituents, but they don't cancel perfectly because in general, the charge clouds, when you solve the Schrodinger equation for the dark atom, are not perfectly overlapping. Only in the case where you have a question.
Yeah, thank you. Just about this Shuffleboard mixing. So we had previously learned, I think in our light dark matter lectures, that whether you have your standard model coupled to your dark U1 or your dark matter coupled to your standard model U1 was a matter of field redefinition. But in this case, both of them are happening simultaneously.
Yeah, that's the interesting thing that's happening here. If I set lambda equal to 0, that would be the standard thing for, I think, a massless photon. Let's see, no, massless photon would be giving me millicharged. Massless dark photon would be giving me. Yeah, anyway, this is something more general.
So in this case, could you redefine your field such that you only have one or the other?
In this case, no, this is the minimal
Okay.
thing. I mean, you could have an accident here where these two things cancel,
Sure.
but
Okay, thank you.
I just got a minute left, but let me mention this cancellation is not perfect. What you get is a form factor that depends on the momentum transfer, call it Q, that's flowing through that photon. And the form factor is the Fourier transform of the charge clouds, the difference of the charge clouds between the dark photon and the dark electron. So those would exactly cancel if their masses were equal, but in general, they won't cancel. And for very small momentum transfer, this is going to go like Q squared. And the interesting thing is that it cancels. There's also a photon propagator appearing in this diagram. So it's interesting that these two things cancel and they lead you to a contact interaction. And so then you get a very simple expression for the scattering of cross-section of protons on dark hydrogen atoms, which is just going like, the important thing here is that it gets enhanced by the size of the atom to the 4th power. So you can get pretty big direct detection cross sections that give you rather strong constraints on epsilon. I think I'll just show that and then we'll go to break. Yeah, actually, this is a reference where the way that they were, these are showing constraints from the direct detection. They're plotting it in the plane of r minus 1, using the fact that if r is close to 1, then you can get a stronger cancellation here. And so they've taken advantage of that to satisfy their constraints. In the dark sector, they've engineered this dark sector to have a significant ionization fraction, because what they wanted was a model where you could address this edges 21 centimeter anomaly that likes to have millicharged dark matter. And so they could get a small fraction, but big enough fraction of military dark matter just by having some of the dark atoms ionized in this setup. So it's just an example of direct detection of dark atoms. And, sorry for going over.
No further questions, then see you tomorrow or around.
Okay.